So some examples of an irrational number would look like this, something that's not repeating and not terminating. Pi. Even though pi doesn't seem like anything, it's a really long number. It's 3.141592 and a bunch of random numbers. There's no really repeating order, and it never terminates, meaning it never ends. Okay? So this is a great example of something that would be considered irrational. Also, getting the square root of a number that you can't really get the square root of. For example, the square root of 3, right? When you type it in on your calculator, it's going to be a bunch of random numbers, probably like 1.7 ... Nothing really repeats, nothing ever terminates. Something like the square root of 37. Okay, that would be around 6.1 or 6.2, and it does not repeat, but it doesn't end. It's a bunch of random numbers. So anything that's considered irrational is basically a decimal that does not repeat and does not end, okay? Or getting what we call the square root of a non-perfect square, okay? So when I can't get the square root, this is also considered irrational. And the sole reason for this is that it cannot become a fraction. So it cannot become a fraction. All right? So now that we kind of have all the terms of what is rational, irrational, everything that talks about what kinds of number there are, let's actually look at example 1. This is on page 47, and I'm going to kind of be going back and forth between this and the printed notes, okay? So example 1 says, which is not a rational number? Now remember, the definition of a rational number is anything that can be written as a fraction. And I'll be kind of honest, all of these are almost looking like they're fractions, except for this one, right? So a lot of times people think maybe this is not the answer. But remember, 0 is a whole number, and a whole number falls under the rational. And that's because you can put this as 0/1, and now it's a fraction. Also, -9, you can put that over 1, and now it's a fraction. So all of these look as though each one of these are rational, but there is one out there that is irrational, and that's this one right here. This is the rare exception. So this is the one that's not rational. And that's because there is a difference between having something like 0/3 and 3/0, okay? 0/3, when you divide it, maybe if you pick up a calculator, you can see that my answer here is 0. But if I was to type in 3 divided by 0 on my calculator, you're going to see that on your calculator it's going to say error, error, okay? And that's because you really can't divide 0 by 3, right? So this is what we called basically an undefined answer. We did see this in our recent lesson, and because it's undefined, this is what we consider irrational. Okay? So even though all of these look like they're fractions, make sure you look at each one of them very carefully. If you ever see that there's a 0 at the bottom, then you can consider it irrational because it is undefined. Okay? So hopefully you understand how rational, irrational, and even the breakdown of what a rational number is. I'm going to go straight into example 2, which is actually pretty different from everything that we've seen so far. Okay? So example 2 looks like this. Now this is not on page 47. Example 2 is on page 48. It's on the next page. And it tells us to convert, it says here 12/5 and 4/11 to decimals. So when it says convert, it wants us to make these fractions into decimals. So what is the rule to making a fraction into a decimal? Okay, so to make a fraction into a decimal, you're going to need to divide. That's right. You're going to have to do some division here. Not necessarily long division, but you are going to have to be dealing with decimals. And I'm going to set up this first one so you kind of get an idea of what I mean when I divide. So how do I set it up? Well, if it helps you out, every time I'm setting up a division problem, my numerator is always going to go inside and my denominator will be going outside. I kind of like to say the guy on top of the world, he's awesome. He lives inside the house. So it's going to look something like this. 12 divided by the guy at the bottom lives outside. I can actually convert this to a decimal and let's see what it will become, okay? So let's see, how many times does 5 go into 12? 5 goes into 12 2 times, and that's because 2 times 5 is 10. And that's what I'm subtracting here. I subtract like normal. 2 minus 0 is 2. 1 minus 1 is nothing. However, this is still not a decimal yet. So to continue as a decimal, what you're going to need to do is place a decimal where there is none, and you place it all the way in the back. However, if you're going to put a decimal here, you need to also put it above. Also, we need to keep going with this. So what we do is we add a 0 and we bring that down. Now I can do 5 divided by 20, and hey, that goes in perfectly. That goes in 4 times. And 4 times 5 is 20. So right there, so for 12 over 5, that's the same thing as saying 2.4. Okay? So that's the answer to the first one. Let's actually work on the next one, and you're going to see why this is interesting, okay? The second one, again, the numerator goes inside, the denominator goes outside. And let's see what this actually looks like. Now, here's the thing. Can 11 go into 4? Well, it can't. So I got to put a 0. I need to make sure that I incorporate a decimal. And if I incorporate 1 down there, I got to incorporate 1 up here. And I put a 0. And how many times can 11 go into 40? Well, 11 times 1 is 11. 11 times 2 is 22. 11 times 3 is 33. Getting pretty close. 11 times 4 is 44. That's too much. So it's got to be 11 times 3, which is 33. Okay? And now when I subtract this out, 0 minus 3 can't do. So I got to borrow from the 4. That becomes a 3. 10 minus 3 is 7. And 3 minus 3 is nothing. Now, when you feel like you can stop there, the only time you know to really stop is if there's a 0 as my remainder, meaning I have no remainder left, or if you notice that there's a pattern going on up here. And let's see if that's the case. Now, if I want to continue, because it doesn't really terminate here, I'm going to include another 0, bring that down, and start it all over again. How many times does 11 go into 70? Well, it goes in 6 times, because 6 times 11 is 66. And I keep going and I keep going in that pattern, okay? So now I'm going to do 70 minus 66. And let me actually fix this up a bit. 70 minus 66, which is 4. I bring down another 0. And now 11 goes into 40 3 times, because that's 33. And then I get a 7. And then I bring down another 0, and then that's a 6 again. Hey, there's kind of a pattern going on here. This is what we call a repeating decimal. And in other words, we know that 4 over 11, equals 0.36 repeating. Now, we don't want to keep writing 36, 36, 36. The way that we show that if something is repeating is we put what's called a repeating bar at the top, to show that both the 3 and the 6 are repeating over and over again. So 3, 6, 3, 6, 3, 6. The next one would be 3, then 6, over and over again. And that's how you convert a fraction into a decimal. Sometimes you might get terminating. Sometimes you might get repeating. You kind of have to work each one out to really see it through. Okay? So that's how you do that. I'm going to go into one more, which is example 5. Okay. And this one is on a different page. So give me 1 second. Example 5 on page 49. And it says the following. It asks which numbers are rational. And they give you a few numbers here. They give you the numbers 5, square root of 3, 4.53. They give you pi over 8. I'm going to have to write some more over here. They give you 0.16 repeating. They also give you 0.34 repeating. And then they give you one that looks a bit funky, so I'm going to have to write it out. 1, 2, 1, 1, 2, 2, 1, 1, 1, 2, 2, 2, dot, dot, dot. Now, let's go over the definition of rational again. Rational means that I can write it as a fraction, right? So there's going to be some obvious ones that we can tell that we can write as a fraction, okay? And the first one that I see might be tempting to maybe say that it's rational is this one, because even though it looks like a fraction, this is not actually rational. And that's because anything associated with pi automatically makes it irrational. Remember, as we wrote back here, an example of something that's irrational is pi. So we know that that is not rational. So pi over 8 and even pi are not rational. However, 5, I can put that over 1. Okay, that's rational. 4.53. You can definitely make it rational as long as it's a terminating decimal, meaning a decimal that ends. That's rational. Also, repeating decimals, and it also says it at the bottom of these printed notes, as you can see here. See, repeating and terminating decimals are considered rational, okay? So that's very important that you keep note of. So I have a repeating decimal here. That's rational. Another repeating decimal. That's rational. Now we're between these two. Now let me ask you, can I get the square root of 3? Not really. This is what we would call a non-perfect square. And just like how I wrote it back here, the square root of 3 is going to be non-repeating, meaning it doesn't really repeat and it doesn't really end, meaning it's automatically irrational. Okay? Now this one looks like it's going in a pattern, right? But it's not repeating in the correct order. So here, if you notice, it's 1, 2, the next number is 1. The next number after this should be 2. When you repeat, it should not necessarily be in a fancy pattern. It should just go back and forth between a couple numbers. So if it's 1, 2, then the pattern should be 1, 2, 1, 2, 1, 2, 1, 2. Meaning this is not really repeating and it doesn't really terminate. So because it doesn't repeat and it doesn't terminate, this is also irrational. So the only ones here that are rational are 5, 4.53, 0.16 repeating, and 0.34 repeating. And that's about it. Those are the ones from there that are rational. All right? So just be mindful that in your homework, you're going to see throughout questions 11 through 20, okay, where they're going to ask you to draw this Venn diagram, and they're going to ask you to put numbers inside of here. So what I'm going to do now is I'm going to just do 3 questions from 11 through 20 right here, right now. So this is straight from your homework 2.1. So let's kind of take a look. I'm going to work on number 11, and number 11 wants us to use the number -6. And what it wants us to do is it wants us to draw our Venn diagram, make sure we label rational, integer, whole, and natural. And then it wants us to put it in the innermost position. In other words, it wants us to put it in the smallest circle possible. So we're going to see where this -6 can go. And we're going to start off with the smallest circle. And that's what I recommend you guys. Always start off with the smallest circle. Can -6 be a natural number? Well, -6 is numbers that you count naturally. So do you count -6 when you're counting how many chairs are in a room? Not really. So it's not a natural number. Is it a whole number? Well, a whole number is just like natural, and they're both positive, so not really. And now we have an integer. Hey, integers are like whole numbers, and they're opposites. Isn't -6 the opposite of +6? So yes, -6 is an integer. When I do my homework, you can just place the number -6 inside of the integer box, like so. Okay? So the next one that I'm going to do is actually number 14. So number 14 looks like this. It has 0.313131 ... Okay? Now, here's the thing. This is a decimal. And I already told you that there are no fractions or decimals for integers, whole, or natural, right? So we already know that because this is a decimal, it's not a natural, it's not a whole, it's not an integer. It's probably either just rational or irrational. Now, if it's irrational, you're going to place that number outside of here, and if it's rational, you're going to place it in the rational bubble. However, does it look like these numbers are repeating? Let's see. It says 3, 1, 3, 1, 3, 1. Yeah, you know what? I think that is repeating. And if it's repeating, it's classified as rational. So I'm going to place in that 0.313131 right in the rational bubble. All right? Now, the last one that I'm going to do is number 18. Is the last one I'm going to do here, which is the square root of 5. Now, if I was to type in the square root of 5, you're going to see that you kind of get a weird number. It's going to kind of look like 2.2 something something something. It's not really repeating, doesn't really end. This is what we call irrational. Now, Mrs. Elliott, there is no bubble or there is no part of the Venn diagram that represents irrational. So to represent it as irrational, you're going to put that square root of 5 off to the side of the Venn diagram, and doing so would classify it as irrational. Okay? So the whole point of this lesson, lesson 2.1, was to identify the kinds of numbers, determining if it was rational or irrational, while breaking down that rational has other names such as integer, whole, and natural.